Okay, Assalamualaikum warahmatullahi taala wabarakatuh. My name is Rajesh Amir Hakimi bin Rajadullah. My metric number is DE210064. Okay, we are from Group 1, Section 3. Okay, here are my group members. Okay, first is me, and then Muhammad Aiman bin Muhammad Yasin, and lastly Ahmad Fikri bin Muhammad Nonaski. Okay, our lecturer name is Dr. Raisham bin Abdul Rahman. Okay, for our project, we choose suspension porcelain insulator for 132 kV. For project background, insulators are frequently shaped to reduce wind resistance. Insulators are a crucial part of the electrical grid, playing a vital role in safely transmitting electricity over long distance. Porcelain is a non-conductive ceramic material known for its high strength, good insulating properties, and resistant to weathering. Porcelain suspension insulator have been around for a long time and remain a reliable and cost-effective solution for many applications. Okay, next is problem statement. First, maintaining insulator performance over time. Long-term exposure to extreme weather condition, pollution, and UV radiation can erode the insulating qualities of materials such as glass and porcelain. Okay, next is improving efficiency and maintenance. Nowadays, technique for identifying insulator issues frequently rely on subjective and consuming visual inspection. The objective for our project is first to design a HV insulator by considering the appropriate method endorsed in the formal literature. Okay, next is to simulate the HV and electromagnetic field distribution to the proposed prototype. The next is to evaluate the performance of HV insulator prototype under various environmental stress. And lastly, to work out of a test set up for appropriate HV testing that consider correct equipment, safety, and practical procedure. The scope of the project is first to analyze the influence of design parameter on the performance of HV insulator. Next is to develop a geometric model of the proposed HV insulator prototype using computer-aided design (CAD) software. Next, identify the climate and environmental variables that are most likely to affect the performance of the HV insulator prototype. Lastly, to develop test scenarios that cover a range of high voltage testing applications. Okay, next we go to technical summary of chosen concept design. Okay, high quality external insulator are necessary to assure the quality of energy delivered through a transmission line. Porcelain insulator have been the dominant kind of outdoor insulation for over a century due to its excellent electrical and mechanical properties. Okay, next is string insulator are typically used as dead end insulator. The string insulator is designed to withstand the tensile load of a conductor in a transmission line. Okay, next is 132 kV is a high voltage that requires enough insulation to avoid electrical breakdown. Connecting 12 these in series increase the overall leakage channel for electricity, which improve the string insulating capacity. Okay, next is creepage and parameter of insulator we use. Okay, first, the system voltage we use is 132 kV, and type of insulation is suspension insulator. For environmental condition, is normal. Length of each disc is 140 mm, and total porcelain disc we use is 12. So the total length of insulator is 1680 mm. So for fitting selection, we use cap and pins. For creepage distance is 5080 mm. For creepage clearance for 132 kV is 7700 mm. Okay, for distance of creepage, we use from the reference that said the creepage distance is around 3 times of the insulator overall. So the total creepage of this project is 3 by 1680 mm. So we get is 5080 mm. So creepage distance is an essential parameter for suspension insulator. It indicates that cumulative length along the length of the insulator on which electricity has to travel from the top and end being the high voltage to the bottom. We go to process flow via simulation. Okay, first is FEM is a process of breaking down large problem into smaller ones. This simplifies the study of the entire problem. Engineers use FEM to build flexible design by using mathematical equation for simulation. Okay, because they provide detailed information on the system behavior under different loading condition and provide significant advantage over other technique of investigation. Okay, next for flowchart. Okay, first we define our geometry. This is from our project prototype. Okay, next is assign material properties such as porcelain, uh, metal, and also air for the condition of the insulator. Okay, next we set the boundaries for the circle air circle. Okay, next for mesh. Next to get the result, we need to mesh the geometry, and then after that we get the result. So the problem solved. And after that, for post processing, we go to visualization result and extract the data, so we can conclude this in report. Okay, for block diagram, okay, first we discuss and choose the type of insulator we use in this project. Okay, in this instant, the block diagram indicate this of shape insulator. Next, we define the specification. Okay, next we go to design and the insulator in AutoCAD. Because AutoCAD has a comprehensive technical illustration of the insulator. So after the simulation, after the design we get in AutoCAD, we go to simulate performance using FEM because FEM can simulate the behavior of the insulator design. And next we go to performance analysis. And lastly, design iteration for the report of the project.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Amar Fikri bin Muhammad Nunaski and number matric AE 20004. Alright, today I would like to present about the methodology of our project. So, the software integration, this project involved the use of computer-aided design, which is CAD software to generate comprehensive technical drawings of the 12-disc porcelain insulated string. The AutoCAD program provided perfect control over all aspects of the insulator design. Okay, we go to the FEMM software. The design of a 12-disc porcelain insulator string for a 132 kilovolt power transmission line goes beyond the physical components. Finite element method, which is FEM software like FEMM, can be used to simulate the electrical performance of the insulator rings. By applying a voltage similar to the 132 kilovolt operating condition, the software can help visualize the distribution of the electric field within the insulator string. By analyzing the electric field distribution, potential weakness in the design can be identified. For example, the software might reveal areas where the electric field is concentrated near the edges of the disc or around metal hardware connections, indicating potential points of concern. Okay, we go to the AutoCAD. This project focused on the design of a critical component for high voltage power transmission lines, a 12-disc porcelain insulated string, to ensure reliable and safe operation and 132 kilovolt. AutoCAD software played a vital role in creating detailed and precise technical drawing of the insulated string. This accuracy is essential for proper functionality and ensures that all discs, pins, and CAD fit together seamlessly. While AutoCAD played a central role in creating the technical drawings, the project might select the appropriate porcelain material with the necessary electrical and mechanical properties for a 132 kilovolt applications. We go to the characteristic of porcelain insulator. First, high dielectric strength. Porcelain is a good electric insulator because of its high dielectric strength, and it is be able to withstand an electric field without carrying the field. This feature is very important to stop the AC current passage through the insulators and effectively separate the conductor from the grounded parts of the transmission line. And we go to the next characteristic, which is high resistivity. Porcelain is a good electric insulator because of its high dielectric strength. It is a poor conductor of electricity, and this high resistivity lead to cutting down leakage current, which is a small current that could flow across the surface of the insulator due to moisture or pollution. We go to the next characteristic, which is relatively high permittivity. It is a significant that permittivity of porcelain is higher than permittivity of open space. Permittivity affects the capacitance option of the insulator, and this in turn may affect the electrical performance of the line. Compared to the other insulating materials, the permittivity of porcelain is not that high, which is not delicate on performance most of the time.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Muhsin and my contact number is DE210097. Okay, let's move to the simulation. This is our simulation for group 1, which is type of insulator is suspension, and the size for single insulator 270 mm times 140 mm. So the stack 1, the length for the stack 1, total we use 12 insulator, 12 disc insulator, which is 1680 millimeter. Okay, let's move to the simulation FDM. Okay, this is our design for the insulator. So the material that we use is metal, porcelain, and air as a condition. Okay, this in the dry condition, sorry, and then we run. Okay, for the result, we can see the highest one is the value that the voltage that we inject, which is 11 k volt, and the bottom one is the grounded. Okay, after that, for the field intensity, the highest field intensity, which is at the after the voltage inject, the highest field intensity, which is at the bottom metal, at the mid metal, which is at the mid metal after the voltage inject, and after the voltage flow to the ground. Okay, for the next, this is a design for the single insulator in wet condition. Okay, okay, we can see here the voltage, the different voltage in dry and wet condition is the same, but the field intensity is a difference. And the highest field intensity that we get 2.4 mega E. Next, for the stack insulator in dry condition. Okay. So for this design, we stack our insulator that we make in a single insulator. So we stack it to 12 discs. Okay, and then we run. Here is the result for the stack insulator in dry condition, which is 1. We set this the voltage 132 kilovolt, and the voltage that inject at the top one is 1.25, and the at the bottom one is the grounded, which is 0 volt. Okay. For the next simulation, which is a stack insulator in wet condition. Okay. The voltage between the dry and wet is not a different one, but for the field intensity, the value for the field intensity is different, which is the wet one is higher than the dry one. Okay. Okay. For this design, we use the surrounding area with air pollution. So we add the property for the air pollution is 100, and we mesh this. Okay. After that, okay. The value for the voltage is the same, but the value for the field intensity is much lower than the dry one when the clear air. Okay, let's move to the wet pollution. Okay. So this is the value for the voltage that will inject in the insulator, and the value for the field intensity. Okay. The value for the field intensity for the dry pollution and wet pollution. So the field intensity in wet condition is much higher than the dry pollution. I think that's all for the simulation. Thank you.
Okay, next we go to the analysis of FEA simulation results. Unexpectedly common that poses a threat to porcelain insulators. These unsung heroes of a high voltage transmission line. Different type of pollution can greatly degrade these essential elements. This section provides a detailed explanation based on theoretical knowledge and analysis. Alright, the first analysis of FEA simulation is electrical stresses profiles on the prototype surface. This project focused on testing a 132 kV porcelain suspension insulator under various conditions. It examined how the insulator performs with high voltage alternating currents, which is HVAC, in both dry and wet environments. A dry environment allow for the highest flashover voltage. A lower creepage distance is crucial in high pollution areas because it provides a larger path for leakage currents, which is reducing the flashover risk. The simulation help predict how an insulator will perform under different electrical stresses and environment factors like wind, pollution, temperature, and humidity. The project also involved analyzing the electrical stress profile on porcelain insulators. It means examining how voltage is distribute along the insulator surface and identifying areas with high electric field intensity that might lead to flashovers or breakdowns. By minimizing high electrical stress through proper insulator design, material selection, and preventive checks, the durability and safety of high voltage electrical system can be improved. Okay, we go to the next analysis, which is highest and lowest point measurement level. To determine the highest and lowest stress levels on a porcelain insulator rated at 1 to 5.4 kilovolt, we need to identify where the electrical potential is most extreme on its surface. The highest stress usually occurs at sharp edges, corners, or points with big changes, which are critical spots for potential electrical breakdowns. Engineering check these areas to ensure the insulator can handle the maximum stress without failing. The lowest stress areas have very low electrical potential, ideally close to 0 volt. These spots are important to confirm even voltage distribution, ensuring the insulator work efficiently. Understanding and optimizing these stress levels is crucial for designing and evaluating porcelain insulators to ensure they operate safely and reliably at 1 to 5.4 kilovolt. Okay, we go to the next analysis, which is a critical area, which is fittings, joints, and attachment. The key area in porcelain insulator with metal caps, such as fitting, joints, and attachment, are crucial for the success of electrical transmission and distribution systems. These are the mechanical part that attach the insulator to support structures like poles or towers. They must ensure a firm connection and evenly distribute mechanical pressure to prevent structural failure. These are where different parts of the insulators or the insulator and metal cap meet. It's important to maintain strong sealing and insulation here to keep moisture out, as moisture can damage the insulator's dielectric properties and cause breakdowns over time. Additional parts like conductor links must be securely fastened to ensure both electrical and mechanical stability while preserving the insulator's insulation properties. Good design is crucial at these key points to minimize stress and prevent rust and ensure long-lasting reliability in various environment conditions. Next, we go to the last analysis, which is for pollution impact and porcelain insulator. There are many different types of pollution, such as dust, salt spray, and industrial smells. These impurities may accumulate and create conductive channel on the insulator surface. When moisture condenses on this layer, it forms a wet path that lowers leakage resistance, allowing more current to flow over the insulator surface. Even a small leakage current can lead to insulator deterioration over time. Combined with flashover event, this can speed up the aging process, shorten the insulator's lifespan and necessitate early replacement. To combat this issue, insulators with larger creepage distance make it harder for leakage currents to flow. This can be achieved by adding ribs to the surface or using larger insulator design. Composite insulators are less prone to pollution build-up and can be performed better in highly contaminated environments. Okay, so we go to the conclusion for our project. This project focused on testing a 132 kilovolt porcelain suspension insulator under various conditions. It examined how the insulator performs with high voltage alternating currents, which is HVAC, in both dry and wet environments. Generally, a dry environment allows the higher flashover voltage. The study highlighted the importance of creepage distance, which is the path an electric current take over the insulator surface. A longer creepage distance is crucial in high pollution areas because it is provide a larger path for leakage currents and reducing flashover risk. Simulations help to predict how an insulator will perform under different electrical stresses and environmental factors like wind, pollution, temperature, and humidity. Okay, for recommendation and for our features, while testing in a controlled setting yields insightful information. Real-world testing can provide a more comprehensive knowledge of insulator performance, and this could entail putting up a test line that is exposed to pollution levels and changes in the environment naturally for a long time. Long-term performance monitoring of porcelain insulators can yield important information on how pollution impacts their lifespan and how they age. This can entail taking regular readings of the surface deterioration, flashover voltage, and leakage current.